Vanakkam. I'm Dr. Gnanachandra, Center for Research and Postgraduate Studies in Mathematics, Ayya, Nadar, Janaki, Ammal College, Sivakasi. In this video, we are going to see about the connected spaces in metric spaces. This video contains the definition of connected as well as disconnected spaces and examples and the rule of connectedness in real line as well as continuity and connectedness. That is connected spaces and relation connecting connected spaces and continuity. Let us enter into the definition of connected spaces. First, let us see what is connected space. Before I enter into the formal definition of connected spaces, I can write M. That is, I can take M is a metric space. M not equal to A union B. Here A and B are subsets. How this A not equal to empty, that's A non-empty, and B also non-empty, as well as A and B are open, A comma B are open, A comma B are open, and one more thing is A intersection B, that is A intersection B equal to empty, that is A and B are disjoint. I have taken a metric space M. That metric space M cannot be written as a union of two non-empty disjoint open sets. Then we say that M is said to be connected. Don't forget this, guys. M cannot be, a metric space cannot be written as a union of two non-empty disjoint open sets. Then that metric space is said to be connected. That means does not exist a separation. Okay, this means that in this space there is no separation. Okay. Then when we say that a space is disconnected, yes, the space M is not connected, then it is said to be disconnected. Okay. Here are some of the examples of disconnected spaces. Why we concentrate about disconnected spaces? Okay, guys, before you enter into the formal example of connected spaces, we first see the examples of disconnected spaces. I have taken a real line, guys. I have taken a real line. Here, just two disjoint intervals, A comma B and C comma D, with the condition here AB and AB less than C. Okay, guys, B value is minimum of C. I have written M equal to A comma B. This and this. So here, this is the metric space. M equal to A comma B union C comma D. This is subspace of R. Okay, guys. Okay. Then under the restriction of usual metric on M, both A comma B and C comma D are open as well as closed, because in a subspace this A comma B and C comma D, closed interval A comma B and C comma D are open, but in the whole space, that is in R, they are not yet open. Okay, guys. Hence M can be written as a union of two non-empty disjoint open sets. This fact says that M is said to be disconnected. Okay, guys. The choice of intervals to be closed in R is not necessarily in the above example. Okay, guys. Okay. Now, next, another one example of disconnected spaces. Any discrete metric space with more than one point is disconnected. Any discrete metric space with more than one point is disconnected. We all know about the discrete metric spaces. A metric space is said to be discrete. The distance between the points is either 1 or 2. The distance is 1 if the 2 points are not equal. If the 2 points are same, that is x and y are same, the distance between x and y are 0. So this is a discrete metric space. And another one property is in a discrete metric space, every subset is open as well as closed. All the subsets of a discrete metric space are open as well as closed. So discrete metric space with more than one point is disconnected. This is another example. See, here I have taken a discrete metric space M. Okay, already I said that discrete metric space contain more than one point. So I have took a subset A is a proper subset of discrete metric space M, because M contains more than one point. So surely A not equal to M. Since M has more than one point, such A exists. I can already say that A is exist. Therefore, A complement is also not equal to empty. Since M is a discrete metric space, both A and A complement are subsets of M. Therefore, M can be written as A union of two non-empty open sets, that is A and A complement. So don't forget guys, A and A complement are both open and closed because both of them are subsets of a discrete metric space. In a discrete metric space, A and A complement union are open as well as closed. Therefore, M equal to A union A complement. A not equal to empty, A complement not equal to empty, and one more thing is A intersection A complement. A intersection A complement equal to A. Therefore, these conditions are satisfies the disconnected metric space properties. Therefore, a discrete metric space with more than one point is. Why? Now, why there is no example for connected space? Wait, guys, I will say. Okay, next one theorem. This is an important characterization theorem for connected metric spaces. Already we saw that M is said to be connected. M cannot be written as the union of two non-empty disjoint open sets. Here another characterization, M is connected. M cannot be written as the union of two non-empty disjoint closed sets. So we can replace open sets by closed sets. Okay guys. And the next one is M cannot be written as the union of two non-empty sets. Here I have taken ordinary sets, not A, not open, not closed. Just I have taken a sets A and B such that A intersection B closure equal to A closure intersection B equal to empty. And another characterization is M whole set and empty are the only sets which are both open and closed in M. So, a metric space M is said to be connected. The only sets which are both open and closed, that is closed, are empty set and whole sets. So, this is a characterization theorem for connectedness. Let us see the proof of this theorem. First, I can assume that M is connected. How to prove that M can be written as the union of two non-empty. M cannot be written as the union of two non-empty disjoint closed sets. Okay, guys. So now I am going to write M equal to A union B in B, where A and B are disjoint closed sets. So guys, yeah, I have not written M not equal to. Here I have written M equal to A union. Since A and B are closed, A complement equal to B and B complement equal to A. Why means this A and A intersection B equal to empty, guys. A intersection B equal to empty as well as A union B equal to A union B equal to whole space. Okay. A union B equal to A. So let us see this by a diagram. This is A and this is B. A union B. Sorry, guys. Yes, this is A. This is B, okay guys, this A union B equal to M, together with this equal to M, and A and B are disjoint, therefore A complement equal to B and as well as B complement equal to A, okay guys. Then M is written as the union of two disjoint open sets, which contradicts the fact that M is connected, therefore this holds. And another one is, suppose M equal to A union B, I have assumed 2 and to prove third one, where A and B are non-empty with A intersection B closure equal to A closure intersection B equal to empty. I took an element X belongs to A closure. Since we have assumed that A union B equal to M and A closure intersection B equal to empty, therefore X belongs to A. I have taken an element X in A closure and proved that X belongs to A. That means A closure is contained in always A is contained in A closure. We all know that. Okay. So together with this, A equal to A closure. That means a set equal to its closure. That means A is closed. Okay. Similarly, we can take A intersection B closure and A union B equal to M. We can prove that B is closed. Hence, M is the union of two disjoint non-empty closed sets, which is a contradictory assumption. And the third implies 4. Suppose we have assumed that the third is not true. Okay, guys. Suppose there exists a non-empty proper subset A of M such that A is both open and closed. So other than we have to prove empty and whole set are the only sets which are both open and closed. Okay, guys. Other than empty and whole set, I have to another set. I have taken another set that is A, that is both open and closed. Okay, and B equal to A complement. I already said that A union B equal to M. Okay, since A is both open and closed, because A is both open and closed, then B is closed as well as open because B equal to A complement. Thus, M equal to A union B. With A closure intersection B, we have found the value of A closure intersection B as well as A intersection B closure equal to A intersection A complement. I took B equal to A complement, so that. So A intersection A complement equal to empty, which is a contradiction to our assumption. We have assumed 3 is not true, but here we get a contradiction to that. Okay, therefore 3 implies 4 is true. Another one is 4 implies 1. Suppose M is not connected, that is M equal to A union B as well as A and B are non-empty, disjoint, open sets. Since A complement equal to B, therefore B is closed in M. Thus B is both open and closed in M. It's a contradiction because in our assumption, empty set and whole set are the only sets which are both open and closed in a connected spaces. But here we have assumed M is not connected. Therefore, we get the characterization theorem of connected space. Okay, guys? Next one is a metric space M is connected if and only if there does not exist a continuous function M from M onto discrete metric space 0 and 1. So, the space contains only 0 and 1. Here, see guys, this is a metric space and this is a function. Here the elements are only 0 and 1. In a codomain, the elements are only 0 and 1. So, M is connected, does not exist, such a continuous function does not exist. This is a theorem. First, I can assume that M is connected. Suppose there is a continuous function F onto, that means this function is onto 0, 1. Since 0, 1 is discrete, therefore singleton 0 and singleton 1 are the subsets of 0, 1. This is a discrete metric space. We all know that in a discrete metric space, every subset is open and closed. Therefore, singleton 0 and singleton 1 are open. We have take A equal to F inverse of 0 and B equal to F inverse of 1. F is a continuous function. Also, we know the characterization of continuity. That means inverse image of every open set is open. We can use this. A and B are open in M. So here A and B are open subsets of M. Since F is onto A and B are always disjoint and non-empty sets. M equal to A union B, which contradiction M, because we have assumed that M is connected. Hence, such a continuous function F does not exist. Converse part, assume that suppose there does not exist a continuous function F from M onto discrete metric space 0, 1. We have to prove M is connected. Suppose we assume that M is not connected, and as usual, M equal to A union B, A and B are disjoint non-empty open sets. Now we define a function F from M to 0, 1. By defining the function, how to here see guys how to define a function f of x equal to 0 if x is an element of A and 1 if x is an element of B. So I have defined a function f of x like that. Here f is onto. We can check this function is obviously onto, and also singleton 0, inverse image of singleton 0, that's empty, and inverse image of singleton 0 equal to again this set equal to A. And F inverse of 1 equal to B, and F inverse of 0, 1 equal to yeah. Okay guys, since this inverse image of each open set is open, therefore singleton 0, 1 is open. Therefore this leads that F is continuous. Therefore, this is a contradiction. See guys, this is the F inverse of empty, not 0. F inverse of empty equal to empty, and F inverse of 0 equal to A, F inverse of 1 equal to B, and F inverse of 0, 1 equal to M. So, inverse image of each open set is open, therefore F is continuous, which is a contradiction because we assume that there does not exist a continuous function. Okay, let us see another problem for a connected metric space. Let M be a metric space. A is a connected subset of M, B is another subset. That B lies between A and A closure. Okay guys, then B is connected. In particular, A closure is connected. This is a problem. We have to prove that a subset B lies between A and A closure is connected whenever A is connected. We have to prove B is connected. Suppose we have assumed that B is not connected. B is not connected means B can be written as a union of two non-empty disjoint open sets. Here B1 and B2 are open in B. Since B is a subset of M, therefore B1 equal to G1 intersection B and B2 equal to G2 intersection B, where G1 and G2 are open sets in M, that B1 and B2 are open in B, this G1 and G2 are open in M. This is a form definition of subspace. Now B equal to B1 union B2, you can substitute the value of B1 G1 intersection B and B2 G2 intersection B, and we get that this B equal to G1 union G2 intersection B. This means B is contained in G1 union G2 intersection B. So B is contained in that. B is a subset of this set intersection B. Therefore, B is a subset of G1 union G2. Also, A is a subset of B. That implies A is a subset of G1 union G2, and A can be written as G1 union G2 intersection A, because A is a subset of G1 union G2. This G1 union G2 intersection A can be written as G1 intersection A and G2 intersection A. G1 and G2 are open in M. A is a connected subset. That means A is a subset of M. Therefore, this G1 intersection A and G2 intersection A are open in A. With we have to find the intersection. That is G1 intersection A intersection G2 intersection A. This equal to G1 intersection G2 intersection A. Here A is a subset of B, therefore this can be written as G1 intersection B. This again written as G1 intersection B intersection G2 intersection B. This is equal to B1 and this equal to B2. We have already assumed that B1 and B2 intersection of B1 and B2 is empty. Therefore, we get that G1 intersection A intersection G2 intersection A equal to empty. We have assumed that A is connected, but their intersection is empty. Also, A is a union of these two open sets. Therefore, either G1 intersection A equal to empty or G2 intersection A equal to empty, because we have assumed that A is connected. So, without loss of generality, we took G1 intersection A equal to empty. G1 is open. G1 intersection A equal to empty. That means G1 intersection A closure equal to empty. You always know that A is contained in A closure. Since B is contained in A closure, that is given in our problem. Therefore, G1 intersection B equal to empty. This leads to B1 is a empty set, which is a contradiction because we have assumed that B1 is a non-empty set. Hence, B is connected. In this problem, we put B equal to A closure. In this case, A closure is connected. Okay, so that problem is completed. And another problem is if A and B are connected subsets of a metric space M such that A intersection B equal to empty, that is, they are disjoint, and prove that A union B is connected. For this, we have defined a function f from A union B to 0, 1 be a continuous function. Since A and B are here, the given A intersection B not equal to empty. Therefore, A intersection B not equal to empty implies that an element x0 belongs to their intersection. And assume that f of x0, the value of f of x0 is 0. Since f is continuous, the restriction map is also continuous. Okay. Therefore, f of x equal to 0 for all x belongs to A, or f of x equal to 1 for all x belongs to A. Since the connectedness of A and the restriction map of F restricted A is not odd. But x0 belongs to A. We took x0 belongs to A intersection B, and f of x0 equal to 0. We have f of x equal to 0 for all x belongs to A. The similar argument we have proved that f of x equal to 0, that is image of x is equal to 0 for all x belongs to B. Hence, f of x equal to 0 for all x belongs to A union B, because x belongs to A as well as x belongs to B. Thus, there does not exist a continuous function on A union B onto 0, 1. By already we saw this problem, and using this A union B is connected. Now, still there is no example for a connected space. Already we have saw a lot of examples that are disconnected spaces. Here, first let us see the connected subsets of R. Then we can go for examples of connected subsets. Okay. The important theorem in the real line is a subspace of R is connected. That is, I took a set A is a subset of R. is connected if and only if A is interval. So in a connected space, that is in R, a space is connected if and only if there nothing but it is an interval. Okay. For that, I have taken a set A that is connected subset of R. I have to prove that A is interval. Suppose A is not an interval. Okay, guys. Because R preserve ordered field property, all the properties for R holds in R holds. Therefore, we took an element A, B, C with the condition that A less than B and less than C. So here A and here B and another element C. With A comma C, these two elements are belongs to a set A and B not belongs to A, because we assume that A is not an interval. Okay, guys. Yes, if it is an interval, A, B, C, all the three elements belongs to that interval. It took an the A is not an interval, so that A and C are belongs to A, but B not belongs to A. We took an open set, the A1, that is, we took a set A1, that is minus infinity B intersection A, and A2 B comma open interval B comma infinity intersection. This interval is open in R, okay, and this intersection is open in A, okay, and B comma infinity is open in R. This intersection, that is B comma infinity intersection A, is open in A. Therefore, A1 and A2 are open in A. And you see, this is the argument given here. Also, A1 and A2 are disjoint because A comma Z belongs to A, okay, and A equal to A1 union A2. So here A satisfies all the condition of, that is A equal to A union A1 union A2 and A1 intersection A2 equal to empty, as well as A1 and A2 are open. Therefore, we assumed that A is not an interval. That means A is connected. But here A satisfies the condition of disconnected spaces. We assume that A is connected. Here, this implies A is disconnected. This is a contradiction. So this contradiction leads to A is an interval. We assumed that A is not an interval. We get a contradiction. Therefore, A is an interval. So converse part is very simple, using least upper bound property, that is supremum. We assume that A is an interval. I have to prove that A is connected. Suppose A is not connected. This is the formal definition of A is connected. A is not connected. A can be written as the union of two non-empty disjoint open sets. Since A1 complement equal to A2 and A2 complement equal to A1, we all know that. Therefore, A1 and A2 are closed in A. Okay, took an element X belongs to A1 and Z belongs to A2. Since A and B are disjoint, obviously X, here see here, A1 complement equal to A2. Here I have took X and Z are disjoint elements, distinct elements. Okay, therefore X not equal to Z. Without loss of generality, X less than Z, because we are dealing with the real line. Therefore, X less than Z. Okay. Although also A is an interval, we assume that A is an interval. Therefore, the elements containing X comma Z, that is closed interval X comma Z, is contained in A. Okay, thus every element of X comma Z either in A1 or in A2, because A equal to A union A2, A1 union A2. Therefore, every element of X comma Z either in A1 or in A2. Here also we can take anyone A1 or A2. Let Y be the least upper bound. That is, I have taken supremum. Least upper bound of X comma Z intersection A1. And I get that Y lies between X and Z. Therefore, Y belongs to X. That is, Y is an element of that. Least upper bound is an element of A. I took an element epsilon greater than 0. By the definition of least upper bound, there exists an element T belongs to X comma Z intersection A1 with the property Y minus epsilon less than T less than or equal to Y. This leads to, because T belongs to this interval, we all know the result. There is an element X belongs to A closure. Therefore, G intersection A not equal to empty, where G is an open set containing S. Using this result, I took an open set Y minus epsilon comma over Y plus epsilon intersection this not equal to empty. Since each open neighborhood of Y intersect X comma Z intersection A1, therefore Y belongs to here. This is the explanation for that. And also this x comma z intersection a1 is closed because x comma z intersection a1 closure equal to closed interval x comma z intersection a1. So y belongs to a1. Similarly, we can use the definition of LUB. In this way, we can get y belongs to a2 closure and a2 is closed. Therefore, y belongs to a2. Y is an element of A1 as well as Y is an element of A2. Therefore, Y is an element of A1 intersection A2. But we assumed that A1 intersection A2 equal to empty, which is a contradiction. Why this contradiction occurs? Because we took A is not connected. Therefore, A is connected. So, in a real line, a subspace A of R is connected if and only if is an interval. Using this result, we can derive R is an interval. We always write a real line as open interval minus infinity, comma, infinity. Okay, guys? So, this is an interval. Therefore, R is connected. So, now let us see the first example of connected space. The real line with usual metric, any interval is connected. So, any interval, that means either open interval or closed interval or a half open interval or half closed interval, any interval with the usual metric in real line is connected. So, next one problem, that is given example to show that subspace of a connected metric space need not be connected. So, a whole space may be connected, but subspace may not be connected. So, for this, let us see, consider R with the usual metric, which is connected. We now only saw that R is connected. Let A be the subspace, which is the union of two disjoint intervals in R. For example, we can take A equal to closed interval 2, 3 and union of 4, 5. Okay, guys. So A is a union of two non-empty disjoint interval. This A is not connected. A be the subspace of R, which is the union of two disjoint interval. Any interval, either open or closed. Here A is not connected. Another example, true or disprove if A and C are connected subset of a metric space and A and B lies between A and C, then B is connected. Guys, A is connected, B is connected, C is connected, or to group B is not connected. To group B is not connected, guys. Here, not connected. So, see, in a real line, we took an example. So, see here, A equal to 0, 1, okay, and B equal to 0, 1 union 1, 2. 0, 1 union 1, 2 and C equal to 0, 2. Okay, C equal to 0, 2. Here both A and C are connected because they are interval. Okay, but B is not connected because here the element 1 is not there. Therefore, B is not connected. Okay, so I can disprove this. See here, the question is true or disprove. Okay, so B is connected. Is given in the. Okay, now we can see the behavior of continuous functions in connected spaces. So first start with the theorem. Let M1 be a connected metric space and M2 be any other metric space. So you see here, this is M1. Okay, another one is M2. This M1 is connected. Okay. M1 is connected and F from M1 to M2 be a continuous function. F is a continuous function. If M1 is connected, then its image F of M1. Okay, F of M1 is also connected. That means F of M1 is a subset of M2, which is connected. That is, this theorem states that a continuous image of a connected set is connected. Okay. Before entering into the proof, see the diagram again. M1 is a connected metric space and M2 is any other metric space and F of M1 is a subset of M2. We can going to prove that F of M1 is connected in M2. That means continuous image of a connected set is connected. Okay, you can take that F of M1 equal to A. So this is nothing but A. Okay, and we can assume that A is not connected. We are going to so we have to prove that F of M1 is connected. But I take F of M1 equal to A. Suppose I have assumed that A is not connected. As per the definition of connectedness, there is a non-empty subset B of A such that A is both open and closed. We already saw in the theorem, if a metric space M is connected, empty set and whole set are the only sets which are both open and closed. Okay, but here A is not connected. Therefore, there exists a non-empty subset other than empty and other than whole set, which is both open and closed. Also, we already assumed that f is a continuous function. B is both open and closed. We know that the continuous characterization of continuity in terms of open set as well as closed set. That means inverse image of open set is open if a function f is continuous, and as well as inverse image of every closed set is closed. So using this fact, we can get that f inverse of B is both open and closed in M1. Here, see here, this is f inverse of M. F inverse of F inverse of B which is both open and closed in M1, but M1 is a connected metric space. So, but you see here F inverse of B is a subset of M1, which is both open and closed, which is the contradiction to M1 is connected, because M1 is connected means the only set which is both open and closed set is empty set and M1 alone. Here another set exists, F inverse of B, that set is both open and closed in M1, which is a contradiction. For contradiction to what? M1. Therefore, our assumption is wrong. That means A is not connected is wrong. Therefore, A is connected. That means F of M1 is connected. Next, there is an interesting theorem in this continuity and connectedness characterization. That means that is the intermediate value theorem. Let f be a real valued continuous function defined on the interval j. Then f takes every value between any two values assumes. That means see here I have fixed an interval j. Okay, that interval is j. I took an element a comma b belongs to j. Then there exists an element f of C that lies between these images. That means C lies between f of A and f of B, and also C equal to some f of x. So I am going to prove C equal to some f of x where x belongs to closed interval G, okay, or any interval J. See here, A comma B, I took an elements, two elements in J with f of A not equal to f of B. Without loss of generality, because we are dealing with real valued continuous function. Our function here is defined in the interval j to r, because this is a real valued function. Therefore, codomain is r. Therefore, f of A is not equal to f of B. F of A and f of B are in elements of R preserve ordered property. Therefore, f of A, we can assume that either f of A greater than f of B or f of A less than f of A. I can took f of A less than f of B. Let C be such that we took f of A, C lies between f of A and f of B. I am going to prove C equal to some f of x. That's all. So, we use the theorem continuous image of a connected set is connected. Since A is an interval is connected. In the real line, every interval is connected. Therefore, J is connected. And F is a continuous function. We use the above theorem. Continuous image. M1 is connected. M2 is any space. F of M1 is connected. Now only we saw that theorem. Using J instead of M1 and M2 as R. We can use that theorem and we get that F of J is connected in R, which is an interval in the real line. Okay. Also, f of A and f of B belongs to f of J. Okay. Then these two, f of J is also in interval. Okay. F of J is also in interval. These two elements are belongs to f of J. Therefore, the closed interval or closed interval f of A comma f of B also is contained in f of J. This means C belongs to f of J, because C is an element that lies between f of A and f of B. Okay. C is an element that lies between f of A and f of B. So C also lies between, C also belongs to f of J. Now, C belongs to f of J means we can write C equal to f of x for some x belongs to J. That's all. So this is an intermediate value theorem. So intermediate value theorem states that f is a real valued continuous function defined on the interval. Then f takes every value between any two values it assumes. Okay. Next one, another problem. This is a problem, a lost problem. Prove that if f is a non-constant real valued function, here also f is a non-function and non-constant real valued continuous function on R, then the range of f is uncountable. So see here the domain is R, and as well as the real valued function means codomain is also R. So f is a function from R to R. Also f is a non-constant function. Okay, we have to prove that range of f is so range of f is uncountable. Using that f is a continuous real valued function. Since R is connected, we all know this, and continuous image of a connected set is connected, therefore F of is connected. R is connected, F is continuous, so F of R, continuous image of a connected set implies F of R is connected. Since we have given F is non-constant, so F is non-constant and connected subset of R. R already is an interval, therefore range of F is already uncountable because R is an interval and F of R is connected and F is non-constant function, therefore range of F is uncountable. So in this video, we saw that what is connected spaces and some of the examples in disconnected spaces and the characterization theorem for connected metric spaces. Then next we can saw that the real line R is connected if and only if it is an interval, and another characterization for F is a function that is connecting discrete metric space 0, 1. And next we saw that the continuity and connectedness, continuous image of a connected set is connected, and the last one is intermediate value theorem. F is a non-constant real valued function. F is a real valued function defined on the interval R. Then F takes any two value, please assume. So this is an intermediate value theorem. At last we proved that every non-constant real valued continuous function on R, the range of F is uncountable. Yes, sir. These all are the some of the exercise problem, guys. You can try it. Prove that closed interval 0, 1 is not connected subset of R with the discrete metric space. So, particular in R with the usual metric, this is connected because this is an interval. This is connected. Here I have given 0, 1 with the discrete metric space. So you can prove this, and also prove that any connected subset of R containing more than one point is uncountable. This also indirectly I have given the theorems and some side here. And that laws to prove that if F from R to R is a continuous function which assumes only rational values, then F is a constant function. So F assumes only rational values. We have to prove that F is a constant function. I have given the clue also. Use the intermediate value theorem and you can get this, guys. You can try this. So up to this, I think you have to understand this concept. Is there any queries?